Hi everyone, for today's lesson we are going to learn about infinite geometric series. Before we get started, I would like you to please complete this warm-up. The warm-up is, what is the horizontal asymptote of the rational function? So horizontal asymptotes are going to certainly be on the free response portion of your final exam, as well as your multiple choice portion of the final exam. So I recommend strongly that you pay attention to this warm-up and you start reviewing your information going all the way back to the very beginning of this semester in Chapter 8. So I'm going to do this warm-up with you. It'll help you to answer some of the questions that are on your final exam review as well. So what is your horizontal asymptote? So a horizontal asymptote is a dashed line that the function approaches, and it just so happens to be horizontal. And we had ourselves a couple of rules pertaining to identifying horizontal asymptotes, and those rules were related to the degree of the numerator and the degree of the denominator. In letter A, the degree of our numerator is 2 because this is y equals 2x squared plus 3. In our denominator, we have 0.5x squared minus 2. And both of them have a degree of 2. And when the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote is going to be y equals the leading coefficient of your numerator divided by the leading coefficient of your denominator. So I'm going to write LCN, and that means leading coefficient of your numerator divided by LCD. And that's going to be your leading coefficient of your denominator. So our leading coefficient of our numerator, that is 2, and our leading coefficient of our denominator is 0.5. And if you were to go 2 divided by 0.5, you'll end up with the number 4. So our horizontal asymptote is located at y equals 4. For letter B, we have ourselves the degree of our numerator being 1, because this is 3x, and our denominator's degree is a 2. This is x squared minus 5. In this problem, we have the degree of the numerator being less than the degree of the denominator. And whenever you have the degree of the numerator being less than the degree of the denominator, your horizontal asymptote is automatically y equals 0. There is no calculation that needs to occur. This is hopefully very helpful and refreshing for you guys, like a good refresher for you to start thinking about concepts that we've talked about a long time ago. So here we go. This is our lesson, our final lesson of Algebra 2 with trig for the entire year. Congratulations, you have made it. And our learning objectives for this lesson is for you to be able to say, I can find the partial sum of an infinite geometric series, and I can find the sum of a geometric series if it exists. So we're identifying the sums of infinite geometric series. Now, if you think about it, these series do not end, yet some of them have a sum, which means that our values, whenever they add up, or we add them up, they will approach a certain number, and that's how you know it has a sum. Sometimes whenever you add these numbers over and over again, they just keep getting bigger and bigger and bigger, and they never approach a number, and that indicates that they do not have a sum. So that's what I mean by whether or not the sum exists, and we're going to talk about that in a little bit greater of detail in just a second. The next learning objective is for you to be able to say, I can use the sum of infinite geometric series to model the swings of a pendulum. So these types of questions will certainly be on your test. So that's something that I want you to make sure that you pay attention to when we get to those types of problems. So some language that we already kind of know is S sub n. This was located in our last lesson. And S sub n, whenever you see that letter n, that means that you're adding terms together, a specific number of terms together. And that specific number of terms are what we call n terms. And if this is S sub n is the first n terms of an infinite series, that means that we're taking a portion of that series and we're finding the sum of it. This is called a partial sum. You're taking a series and you're only adding like the first 5 terms of it, even though it's a series that continues forever and ever. Whenever you just take a portion of it and you find the sum, we call that a partial sum. Now, partial sums, which that's all that we can do because you can't just keep adding the same numbers or add numbers over and over and over and over and over again because you'll never end with adding. Some of these partial sums of an infinite geometric or a neither series may approach a limiting value. And that is what this lesson is about. Sometimes a sum will approach a number. Like if you were to add the first term, the second term, the third term, the fourth term, eventually it'll reach the number 1 or the number 5. And those values kind of approach an asymptote, just like what we learned in chapter 8, if we were to graph all of those functions. Now there are other partial sums of an infinite arithmetic series that do not approach a limiting value. That means that it continues to get bigger and bigger and bigger and bigger and bigger until it finally reaches infinity. And if you notice that your sum just keeps getting bigger and it's only going to approach infinity, we call this no sum. It doesn't approach a specific value, so we just say that it doesn't reach a specific sum. We call it no sum. Notice that I have the word may here, so that means that there's going to be conditions for whenever we're looking at the partial sums of infinite geometric or neither series. For this lesson, we're just going to stick with the geometric series. We are not going to be looking into all of the rules that go with neither series. That's something that you will learn about later on in your future math courses. So let's go ahead and talk about partial sums. So if we were to look at the infinite arithmetic series of 2 plus 4 plus 6 plus 8 plus 10 plus ... indicating that that would continue forever and ever, we would need to describe what happens to the partial sums. What number does the sum appear to approach? Well, looking at our first term sum is going to be 2. 2 plus 4 is 6. 2 plus 4 plus 6 is 12. 2 plus 4 plus 6 plus 8 is 20. 2 plus 4 plus 6 plus 8 plus 10 is 30. So what I did is I took a piece of my series and just kept adding on the next term to see if it approaches a number. And we're going from 2 to 30 in a matter of 5 terms. And it appears as if these numbers are not approaching a specific value. So because it doesn't appear to be slowing down any, if I were to add the next number, which would be 12, we would now have 42, and it's not approaching a certain number. So when it comes to arithmetic series, as n increases, which n is the number of terms that you're adding together, as the number of terms that you're adding together increases, the sum increases quickly. And it increases quickly without a clear ending point. Like it doesn't appear as if we're going to stop once we reach 1 million, something to that effect. This sum approaches infinity as n increases. And if it approaches infinity, that means that we call it no sum. It has not reached a specific value, a specific sum. But, so that is an arithmetic series. So anytime that you are given an arithmetic series, you automatically know you have yourself no sum if it's an infinite geometric series. If it's, infinite arithmetic series. If you have a finite arithmetic series, then yes, you would have a sum, and we would use that formula that we learned in the last lesson in order for us to come up with our sum. Now let's go ahead and look at letter B. In letter B, we want to consider the infinite geometric series, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 or 1/32 plus ... So if we were to look at what happens for our partial sums, for S of n is equal to 1, 2, 3, 4, and 5, we have 0.5, 0.75, 0.888, 0.94, 0.97, if we were to add all of the first 6 terms, that means after 1 over 32, we would add a 1 over 64. Continuing on with that pattern, that sum adds up to 0.984. And if we were to add the first 7 terms together, our sum would equal 0.997. So progressively, our sum is approaching a specific number. If we were to graph it, if we were to let n equal your x value and your sum equal your y value, and we were to plot the points, eventually these will approach, because this is an exponential function, it'll approach a horizontal asymptote, and that asymptote is located at 1. So these values are approaching the number 1. The more numbers that we add together, the closer to 1 we will get. So that's what we want to write down. S sub n appears to approach 1 as n increases. So as we add more and more numbers together, we're going to see that our sum is going to get infinitely close or infinitely closer to the number 1. So how do you know what number that value is going to approach? Well, mathematicians came up with a rule, a formula that we're going to be talking about. So there's some conditions that go along with that, with this rule. This rule is S is equal to a sub 1 divided by 1 minus r. And this is the sum of an infinite geometric series, where our first term is a sub 1 and our common ratio is r. Notice that in this rule, there is no s sub n. There's no little n next door to the s. And that's because we're not just adding a specific number of values together, we're adding all of them. And mathematicians came up with this rule. Now, in order for us to use this rule, there are some conditions. So it says right here, the value of the partial sums approaches, the value that the partial sums approaches is called the sum of the infinite geometric series. Like in this case, all of our values approach the number 1, and that number 1 it represents the sum of our series. This sum can be calculated using the formula that I just talked about. This sum can be calculated as long as the common ratio has an absolute value that is less than 1. So what that means is that in order for us to use this rule, you have to ask yourself the following question. First of all, is this geometric? So I'm going to write down right here, has a sum versus does not have, or so versus no sum. So I'm just going to write like a little table right here. First of all, is it geometric? You have to verify that. That's the first thing that you have to ask yourself. Is it geometric? And if that's the case, cool. It means that it could have a sum. Next, you would need to have the absolute value of your r value being less than 1. If you notice that it is geometric and the absolute value of r is greater than or equal to 1, then you have yourself no sum. So you need both of these conditions in order for you to have a sum. Also, if you have, you'll have no sum if it's geometric and the absolute value of r is greater than or equal to 1, or if it's arithmetic. If you notice that the series that's given to you is arithmetic, then you automatically have no sum and there's nothing for us to talk about. So, in an infinite arithmetic series, so if we're talking about an infinite arithmetic series, that means it has a common difference, not a common ratio. This series has no sum. And that's because their partial sums will never approach a single value. And because it doesn't approach a single value, it'll approach infinity. And because infinity is not a specific number, we call this no sum. So here's our little rule that I talked to you about. And once again, I have that the common ratio needs to be less than, the absolute value of your common ratio needs to be less than 1. If you notice that in a geometric series that your absolute value of r, which means some of your r values are going to be negative and you'll have to take the absolute value of it to analyze it properly, then that means you get to use your formula. If you notice that the absolute value of r is greater than or equal to 1, then the series has what we call no sum. So let's go ahead and look at letter A. Looking at letter A, we have the summation going from 1 all the way to infinity of 0.8 raised to the I minus 1 power. So right away, we can see that this is geometric. Why? Because of the fact that it's an exponential function. So we automatically know, number one, that this is geometric because this is exponential. Cool. So that's geometric. The next thing we need to do is we need to analyze our r value. Is the absolute value of r less than 1? So my r value in this case is 0.8. And 0.8 is indeed less than 1. So cool. That means that it has a sum. So now, in order for us to identify what our sum is, we're going to use the formula s is equal to a sub 1 divided by 1 minus r. Now, what I do not know is I do not know my first term. So I need to know what my first term is. So that means I'm going to let I equal 1 in order to help me do that. So I equals 1 is what I'm going to substitute into my rule. So I'm going to write a sub 1 is equal to 0.8 raised to the 1 minus 1 power. 1 minus 1 is 0, and anything to the 0 power is 1. So my first term is 1. So now I can write out my sum. My sum is going to be 1 divided by 1 minus 0.8 because that's my r value. If this was a negative r value, we would have to be very careful with our signs. So now I'm just going to put this into my calculator. And when I put it into my calculator, you're going to want to put the denominator into parentheses in order to establish that 1 minus 0.8 is indeed your denominator. And when you do that, you end up with 5 as your answer. So that means that if we were to come up with all of the terms of this sequence, add them together as a series, all of those numbers would add together and equal 5. They would eventually approach the number 5. Let's go ahead and look at letter B. So for letter B, we're going from 1 to negative 3/4 to positive 9/16 to negative 27 over 64. Well, the first thing we need to do is we need to verify that this is indeed geometric. So we need to figure out what are we multiplying by each time in order to get to the next number. So if I were to ask myself what times 1 equals negative 3/4, that's going to be times negative 3/4. So now I'm going to ask myself, what is negative 3/4 times negative 3/4? And that is positive 9/16. So it appears as if we are indeed multiplying by negative 3/4 each time in order for us to get to our next number, which means yes, this is geometric. The next thing we need to do is we need to ask ourselves, is the absolute value of r less than 1? Well, my r value in this case is negative 3/4. The absolute value of negative 3/4 is positive 3/4, and positive 3/4 is indeed less than 1. So that means, yes, this does have a sum. This series has a sum. So now I'm going to use my rule. I have s is equal to a sub 1 divided by 1 minus r. What's cool is that I do know what my first term is. They gave it to me. My first term is 1. So I'm just going to say s is equal to 1 divided by 1 minus my r value, which is negative 3/4. Please be careful with this type of problem. You're going to need to make sure that you make that negative a positive. So this is going to be 1 divided by 1 plus 3/4. And I would put your entire denominator into your calculator using parentheses. And when you do that, you end up with a decimal that you can use math enter, and you end up with 4/7. So once again, what I'm doing here in my calculator is I'm going 1 divided by parentheses, and I'm going 1 minus parentheses negative 3/4. And then I'm closing the parentheses to establish that is my entire denominator. I end up with a decimal, and I can use math enter to get 4/7 as my answer. So that is what I'm doing. Please feel free to clean up this problem as much as you want before entering it into your calculator. It will not harm you. And finally, letter C. This is written in exponential form, so the first thing we need to do is establish that this is geometric, and indeed it is. The next thing we need to do is we need to ask ourselves, is the absolute value of r less than 1? Is 5/4 less than 1? It is not. So because it is not less than 1, the r value is not less than 1, then we automatically have to say no sum, and there is no other work for us to show. The next 3 problems, I would like you guys to please go ahead and try those problems prior to coming into class. So I have D, E, and F boxed out, and that's what we're going to work on next time I see you. We have 2 more examples, and then we are done. And problems like these will indeed be on your Chapter 12 test. So please make sure that you feel comfortable with working with each type of problem. It says a person is given 1 push on a swing. On the first swing, so that means the very first swing that person actually went up, the person travels a distance of 4 feet. On each successive swing, the person travels 75% of the distance of the previous swing. We want to figure out what is the total distance that the person swings. Well, what they gave us here is actually a geometric problem. It's a geometric situation. Why? Because I have my a sub 1 is equal to 4. That's how far I went back on the very first swing. And then the person is traveling 0.75% of the distance. So if we were to analyze what the total distance would look like, that would mean that we would start off with the number 4, and then we'd add 4 times 0.75, because the next swing was 75% of, and that word of indicates multiplication. So 0.75 times 4, plus whatever that value is, I'm going to multiply it by another 0.75. So that's 0.75 times 0.75, or in other words, 0.75 squared. Plus, I would multiply by 0.75 again. So that would be 0.75 to the 3rd power, plus ... So as you guys can see, we're working with exponents. This is an exponential function, an exponential situation, and that indicates, number 1, that this is geometric. And because it's geometric, we now need to look at our r value. My r value in this case is 0.75, and 0.75 is indeed less than 1. So that tells me that I do have a sum. And what's nice is that I already know what my first term is. So I have s is equal to my first term, which a sub 1 is equal to 4, and my r value is 0.75. So that's going to be 4 divided by 1 minus 0.75. And I can put that whole thing into my calculator, making sure I put my denominator into parentheses, and I end up with 16 feet. So that means that this person is going to travel a total of 16 feet throughout the entire swinging process. Now, letter B says, suppose the person travels only 3 feet on their first swing. What is the total distance that the person swings? So everything else is still going to be the same, only this time we now have a sub 1 equaling 3. So I'm going to identify my sum of saying 3 divided by 1 minus 0.75 instead of 4 divided by 1 minus 0.75. And if you were to put that into your calculator, making sure you put your denominator into parentheses, you're going to end up with 12 feet. So that means that this person's going to travel a total of 12 feet as they swing back and forth. Here's our last example. It says a pendulum that is released to swing freely travels 18 inches on the first swing. That's our ace of 1. On each successive swing, the pendulum travels 80% of the distance of the previous swing. We want to figure out what is the total distance of the pendulum. Well, if you guys can, I know it's kind of tough to read, but from the ball or the pendulum is going to swing back and forth 16, and then this is 16 times 0.80 because that's 80%. Then we have 16 times 0.80 squared, and then we have 16 times 0.80 cubed. And we would continue on with that, and we would add these values together in a series. So once again, is this geometric? Yes, it is, and that's because it's exponential. Second thing we need to ask ourselves is the absolute value of r less than 1. And yes, 0.8 is indeed less than 1, so that means a sum exists. We know that ace of 1 is equal to 16, and our r value is 0.8, so my sum is going to be 16 divided by 1 minus 0.8. Now, another strategy that you can use instead of just putting this into parentheses, the denominator into parentheses, is to simply calculate what is 1 minus 0.8, and that's 0.2. And so it might be easier to put into your calculator 16 divided by 0.2, but nonetheless, what you're going to end up with is 90 inches. This pendulum will travel a total of 90 inches. And that is the end of this lesson, as well as all of the lessons for Algebra 2 with Craig. If you have any questions over anything, please make sure that you contact me, you email me. Otherwise, I hope you have a wonderful day.